All right, so this video, we're continuing 5.3, and we're just gonna do some practice problems. These practice problems are not part of a grading assignment, so you're welcome to look through all or part of this assignment until you understand what you're doing. But it's just gonna give us some more practice with all of this. So first question, it says, an experiment involves tossing a single die. So we're talking about a six-sided die. These are some events. Event A is to observe a 2. Event B, even number. Event C is a number greater than 2. And let's see, D, observe both A and B. E is to observe both A or B, or both. And F is to observe both A and C. So the first thing it wants us to do here is that list the simple events in the sample space. So simple events, if I come back here to my notes in 5.2.1, it says a simple event is an event that includes only one element. It can be called a simple event. For example, in a coin sample space, the event 2 tails is a simple event because only one element of the sample space is in this event. So in here, they're talking about when you flip a coin twice, the results are, they're up here. I'll rewrite them again though, so we can talk about it. Results are I can get 2 heads, then a tails, then a heads, or a tails and a tails. These are all of my possible events in my sample space. So the event of getting heads and tails is not a simple event because there's 2 outcomes that satisfy that event. The event getting 2 tails is a simple event because there's only one outcome in my sample space that satisfies that event. So coming back here, in order to do this, the first thing I actually want to do is I want to write out my whole sample space. If I'm rolling a die, my sample space is going to be all of my possible outcomes. If I'm rolling a die, I get either a 1, a 2, a 3, a 4, a 5, or a 6. These are my possible outcomes for my sample space, all of my possible outcomes for my sample space. And these are my list of events, A, B, C, D, E, and F. So which of these 6 events is a simple event? Which one only has one outcome that satisfies it in the sample space? Well, A does. Observing a 2. There's only one way I can observe a 2 when I roll a die. B is not a simple event. Observing an even number, there are 3 outcomes that satisfy that event, not 1. So event B is not a simple event. Event C, observe a number greater than 2. This is not a simple event. There's 1, 2, 3, 4 events that would satisfy, or 4 outcomes, sorry, that would satisfy that event. So event C is not a simple event. D, observing both A and B. So when it is a number 2 and it is an even number, how many outcomes are both even and are the number 2? Only one outcome is both even and is the number 2. So event D is a simple event. Event E is to observe A or B or both. So A is a 2 and B is an even number. If I'm looking for either of them to occur, I would be looking for 2 or 4 or 6. There's 3 outcomes that satisfy that event, so event E is not a simple event. And lastly, observing both A and C. A is a 2, and C it says a number greater than 2. Well, here's 2, and these are the numbers greater than 2. These 2 events do not overlap. They are mutually exclusive. So it's impossible for them to both occur at the same time. Therefore, the probability of both A and C is actually 0. There are no outcomes that satisfy both events. So the probability of F is 0. So this is also not a simple event because it doesn't have just one outcome. It actually has none. So our only simple events are A and D. Next, it says list the simple events in each of the events A through F. List of the simple events in each of the events A through F. With A and D. Okay, so I guess it was a weird way to put it for me, but they're basically looking for the outcomes within each of those events. So like for event A, go ahead and write this up here. For event A, our only outcome would be 2. So we could say the event of observing a 2 is a simple event. So the simple event within that event is the event that we see at 2. B, observe an even number. So we could break that down into 3 different events, 2, 4, or 6. C is their observing a number greater than 2. There are 4 outcomes in that event. So to break it up into simple events, we could say 3, 4, 5, or 6. D was already a simple event. It was just 2. E, observe an A or B or both. So again, that's 2, 4, 6. So I could break up this complex event into 3 simple events. And lastly, F, observing both A and C was impossible. And we actually call this the empty sample space. When there's no outcomes that satisfy an event, it's called an empty space. And again, the reason that's empty is because A and C are mutually exclusive events, which means they cannot occur at the same time. All right, part D. What probability should you assign to the simple events? So for each of these simple events, we're talking about one number being rolled. So like even in event C, there are 1, 2, 3, 4 simple events that we can break this complex event into. So if I was treating each of these numbers as its own individual event, every number of the die that I roll has the same probability, 1 out of 6. So the answer to number C, I would say, is just 1/6. The probability of drawing a 1 or a 2 or a 3 or a 4 individually, they're each 1 out of 6 possible chances. So 1 out of 6. Part D, calculate the probabilities of the 6 events A through F by adding the appropriate simple event probabilities. So let's see, the probability of A is just equal to the probability that we roll a 2, which is just 1/6. The probability of B is equal to the probability that we roll a 2 plus the probability that we roll a 4 plus the probability that we roll a 6. Those are our 1, 2, 3 simple events that make up this whole event B. So we add those up. 1/6 plus 1/6 plus 1/6 is 3/6, which is 1/2. We do the same thing for all of our other ones. The probability of event C is a probability of a 3 plus a 4 plus a 5 plus a 6. So that's 1/6 plus 1/6 plus 1/6 plus 1/6, or 4/6, which is 2/3. Probability of event D is just the probability of 2 again, which is still just 1/6. The probability of event E is a probability that we get a 2, plus a probability that we get a 4, plus a probability that we get a 6. So that's 1/6 plus 1/6 plus 1/6, which is 3/6, or 1/2. And lastly, E, we already said, is an empty space. The probability of F happening is still just 0. All right, next question. A particular player hit 70% of her free throws. When she tosses a pair of free throws, the 4 possible events and 3 of their associated probabilities are as given in the table. A, find the probability that the player will hit on the first throw and miss on the second. The probability of a hit first and we said miss second? Yes. All right, so we know with these and probabilities, we're going to be multiplying the probability of the first one times the probability of the second happened, given that the first had happened. And of course, if these events are independent, then the probability, the conditional probability in the second part will be just equal to the probability that they missed the second time. So let's see. We got outcome of first free throw, hit, hit, miss, miss. Outcome of second free throw, hit, miss, and the probability is over here. So it looks like we've actually got this whole thing set up for us already. The probability that she hit the first time and then missed the second time. Oh, that's what we're looking for right there. Okay, well, remember the sum of all of our probabilities would have to be 1. The sum of all of the possible events, the sum of all of the possible outcomes in any sample space must always be 1, because 1 is 100% of all of our outcomes, right? So let's just make sure. Is this all of our possible outcomes? Hitting both times, missing both times, hit first, then miss, hit, miss first, then hit. I can't think of any other way that this could go. So these 4 probabilities should all add up to 1. So I guess I don't need this. Let's see, 0.49 plus 0.21 plus 0.09 plus what is 1? So I'll do 1 minus those numbers. On my calculator, and it tells me that that has to be 0.21. So the probability of a hit and then a miss is 0.21. Part B, find the probability that the player will hit on at least one of the 2 free throws. So we look at all of the events which have a hit. At least 1 hit, so it can have 2 also. So there we go. We want the probability that she hits both times, or that she hits then she misses, or that she misses then she hits. And with those types of combined probabilities, we just need to add up their individual probabilities, which this one again was 0.21. So 0.49, 0.21 plus 0.21. Oops. 0.21 plus 0.21 plus 0.49 is 0.91. So the combined probability that she hits at least once is 0.91. We also could have looked at this a different way. We could have said the probability that she gets at least 1 hit is equal to the complement that she misses both times. Think of it. If she doesn't make at least 1 hit, then she's going to be missing both times. So another way I could have approached this, I could have said the probability of getting at least 1 hit is equal to 1 minus the probability that she misses both times. So that would be 1 minus 0.09, which again is 0.91. You get the exact same answer. You can imagine where it might be easier to use the complement instead of adding things up. We only had to add up 3 numbers to get the answer in this problem. But if I needed to add up, like, say, probabilities from like 49 out of the 50 states, it might be easier to do 1 minus the probability of something happening in just 1 state. Let's look at part 3. 3 people are randomly selected from a voter registration and driving records to report for jury duty. The gender of each person is noted by the county clerk. A, list the simple events. So it looks like all we're interested in here is gender. So a simple event is male or female. Okay. Voter registration and driving records don't recognize non-binary genders, unfortunately. So let's move on. B, if each person is just as likely to be a man as a woman, what probability do you assign to each sample event? Okay, just as likely, that's a probability term right there. That means their probabilities are equal. And the total probability has to be 100%. So what's 100% divided by 2? 50% each. The probability of a male is 0.5, and the probability that the person is a female is also 0.5. C, what is the probability that only one of the 3 is a man? So we're randomly selecting 3 people here. So we want to know what is the probability that we get a man and you get a man a second time, and you get a man a third time, MMM. Well, the probability that we select a man the first time isn't really going to affect the probability that we get a man the second time, because there's probably so many men in this state here, it's not really going to affect the probability if we take one out. So to get this combined probability, we're going to treat these like independent events and just multiply them. The probability you get a man is 0.5 times the probability of another man is 0.5 times the probability of a third man is also 0.5. So 0.5 times 0.5 is, oops, 0.125. So the probability of randomly selecting 3 men, a man and a man and a man again, is 0.125. And we get that by multiplying their individual simple probabilities. And then part D, what's the probability that all 3 are women? Well, the probability to get a man is the same as the probability of a woman. So it'd be the exact same. The probability of getting 3 women is also 0.125. Next question. Four equally qualified runners, John, Bill, Ed, and Dave, run a 100-meter sprint, and the order of finish is recorded. A, how many simple events are in the sample? So all we're recording here is the order that they come in at. So we have 4 people put into 4 different places. So I could write all these out here. It could be JBED or JBDE or JEBD or JEBB and so on. Or we could remember how we did permutations from Algebra 2. Also, if you don't remember permutations, I think we're going to go over that some more later on. I'll have to look at what Apex has. But really quick, we're ordering 4 people into 4 places. So how many people are there for position 1? 4. There's 4 different people who can be in position 1. Okay, so after the first person crosses the finish line, how many people can get second place? 3. After one person has crossed the finish line, there's only 3 people left to get second place. How many people are left to get third place? 2. After the first person and the second person have crossed the finish line, there's only 2 people left to possibly get third place. And then fourth place. How many people are left to get last place? Just 1. So there's 4 people possible that can get first place. After that has occurred, we only have 3 possibilities for second, and then 2 possibilities for third, and then 1 possibility for fourth. So how many total permutations do we have here? We just multiply these together. Remember that we call this a factorial. It's 4 factorial. So 4 times 3 times 2 times 1 is 24. There are 24 simple events in this sample space, meaning there's 24 ways that these 4 people can place in this 100-meter sprint. Part B, if the runners are equally qualified, what probability should you assign to each simple event? Well, if they're all equally qualified, then the probability of them getting in any order is all going to be the same. So we would take 100% and divide it into 24, or 1 for probabilities, 100% of the decimal is 1 out of 24 possible permutations. Part C, what is the probability that Dave wins the race? Well, how many different ways can Dave come in first place? So now we're saying first, second, third, fourth. So now we're saying we only have 1 option for first place. It's guaranteed to be Dave. So the other 3 people can make second place, leaving 2 people left to get third and 1 person for fourth. 1 times 3, oops, times 2 times 1 is 6. So the probability that Dave wins a race is 6 out of 24 total possible ways that they can place. 6 out of 24 is the same thing as 1/4. Part D, what is the probability that Dave wins and John places second? So again, now we're limiting our orders even more. We want Dave to win first and John to win second. So now we have one possibility for first place and one possibility for second place, which leaves two people. Two people can get third, and then after that person gets third, there's only one person left to get last place. So how many ways can this happen? Twice. We can even write this one down because it's fairly small. Dave, John, Ed, Bill, or Dave, John, Bill, Ed. There's only two ways it can happen. So that's 2 ways that they could place out of 24 total ways they could place. So 2 out of 24, or 1 out of 12 if we simplify that. And last one, what is the probability that Ed finishes last? So probability that Ed finishes last is, again, I'm going to look at it this way: first, second, third, fourth. So the first thing we know is guaranteed Ed's going to finish last. So that gets rid of one of our 4 racers. So there's only 3 left who can take first place, and then 2 left to take second place, and then 1 last to take third. So 3 times 2 times 1 times 1 is 6. There's 6 different ways that Ed could finish last. Let's just see if we can write all those down real quick. We had John, Bill, Ed, and Dave. So we could go John, Bill, Ed, Dave is last. Or no, we got Ed last. Ed last. Dave, Ed. Let's see, John, Dave, Bill, Ed. We wanted 6. Let's see if we can get all 6. Just because. Bill, Dave, John, Ed. Bill, John, Dave, Ed. Dave, Bill, John, Ed. Dave, John, Bill, Ed. 1, 2, 3, 4, 5, 6. There they are. There's all 6 ways I could place where Ed would be in last. So I could write all of those down like I just did, count them up, and then divide by 24. But I think using this is our fundamental counting principle, we called it back in Algebra 2, to find how many there is in each thing is pretty easy when we're ordering things like this. So again, that was 6 out of 24, which is 1/4. Let's get another problem. 5. In a genetics experiment, the researcher mated 2 Drosophila fruit flies and observed the traits of 300 offspring. Wow. Okie dokie. The results are shown in the table. So let's look at eye color. Normal eye color and vermilion eye color. Very specific. This person's got an interesting hobby. It says one of these offspring is randomly selected and observed for 2 genetic traits. Or for the 2 genetic. Oh, I see, eye color and wing size. So A, what is the probability that the fly has a normal eye color and normal wing size? So let's see, out of 300 offspring, the number of flies that had both normal eye color and normal wing size is 140. So that's 140 out of 300 total offspring. And I can put that in a calculator and get that as a decimal. It is 0.4666666 repeating. So about 0.467. Part B, what is the probability that the fly has vermilion eyes? So again, there's 300 total offspring. How many of them have vermilion eyes? I see 154. I have to add the 2 up because we're not interested in wing size here. So the total that have vermilion eye color is 154. That's 3 plus 151 out of 300 total offspring again. So that's 0.513333 repeating. So I'll put 0.513. And lastly, part C, what is the probability that the fly has either vermilion eyes or miniature wings or both? Honestly, just so it's you're aware here, they don't even need to say both necessarily. If somebody has vermilion eyes or miniature wings, we're going to assume that it'd be okay for them to have both also. So let's see. The probability they have vermilion eyes or miniature wings. Okay, so you can see when I circle those two possibilities, we do definitely have an overlap at 151. I want to make sure I only count these 151 once and not twice. So we'll do 6 plus 151 plus 3, which gives us 160, doesn't it? 160 exactly, out of, again, a total of 300 fly offspring. So 160 divided by 300 is 0.5333 repeating, so 0.533. All right, next one, make sure you remember you can pause if I go too fast here. So number 6, an experiment consists of tossing a single die and observing the number of dots that show on the upper face. Events A, B, and C are defined as follows. Event A, observe a number less than 4. Event B, observe a number less than or equal to 2. And event C, observe a number greater than 3. This is a fairly small sample space, so it might be helpful to just real quick write down the outcomes that satisfy each of these events. Okay, again, we're rolling a 6-sided die. So my sample space, I'll actually just write that up here just because. Sample space is again 1, 2, 3, 4, 5, 6. So event A, observe a number less than 4. That would be 1, 2, or 3. Notice it does not say less than or equal to, just less than 4. So 1, 2, or 3. B, a number less than or equal to 2, so that would be 1 and 2. And C is a number greater than 3, does not say equal to, so that's only 4, 5, and 6. All right, so let's see what we need to do now. It says find the probabilities associated with these compound events using either the simple event approach or the rules and definitions from this section. So A, it says S. That's kind of weird. It says, remember S? S is for sample space. So what's the probability that we get anything in the sample space? Well, that should be 1. The probability of the sample space occurring should always be 1. We're guaranteed, if otherwise it wouldn't be called the sample space because the sample space has to include all possible outcomes. All right, next one, the probability of A given B. That was the probability of, sorry. So the probability of A given B, the probability that we have a number less than 4, given that we have a number less than or equal to 2. So again, that's a probability of A and B over the probability of B, right? I think so. Yeah. So the probability of A and B, well, there's 2 outcomes I see in both A and B. That's the 1 and the 2. So 2 out of 6, 1/3. Over the probability of B, which is still, again, just 1 and 2. 2 out of 6, which is 1/3. So again, we get 1. Why did we get 1 there? Why is this a guaranteed event? Well, let's look at what we have. It says the probability of A given B. So the probability that we observe a number less than 4, given that we have a number less than or equal to 2. Well, if we know that we have a number less than or equal to 2, the only things it can be is 1 and 2. And both 1 and 2 are less than 4. So this is a guaranteed sequence of events. If I have a number less than or equal to 2, I know I have a number less than 4 because they are completely overlapping. So that's why we got a 1. Great use of that equation though, I think. Probability of event B. Again, event B, we already have it drawn up here. There's 2 outcomes out of 6 total outcomes. That's a probability of 1/3. And now it looks like we have some intersection questions. The probability of the A intersect B intersect C. So those are our and questions. We want, or sorry, yeah, our and questions. We want those things to happen at the same time. The probability that there's an outcome satisfies all 3 events. So usually we would multiply the probabilities as long as they are independent of each other. So let's see, the probability of, all right, so looking at my events here, I can see right away that there's a problem. I'm looking for the probability that all three of these events occur at the same time. And if I look at my first two events, that seems totally possible. I have two outcomes in event A and B that occur at the same time, 1 and 2. But when I add an event C, I see a problem. None of my outcomes in event A or B satisfy event C. So it's impossible to satisfy all three of these events at the same time. So the probability of all three events occurring at the same time, the probability of all three events intersecting is 0. And if I were to try to move on and maybe use the equation we had, I should also get 0. Remember, for intersections, we take the probability of the first event and multiply it by the conditional probability of the second. So I would probably break this up and say the probability of A intersect B, and then intersect that one with C. So let's say the probability of A intersect B would be the probability of A times the probability of B given A. So that would be probability of A, there's 3 events out of 6, so 1/2. And probability of B given A would be, let's see, probability of B given A. So if I look at A, there are 3 total outcomes and 2 of them satisfy B. Oops, that's 2 out of 3. So the probability of A intersect B would be 2 out of 6 or 1/3. Okay, but now what if I intersect that with C? Let's call this event G just for a placeholder. So the probability of event G intersect event C. So that would be the probability of G, which is 1/3, we just said that, times the probability that event C happens given that event G happens. And again, we're expecting to get 0 here, but I'm just going through the process. So probability of event G, that's the intersect of A and B, is 1/3. And the probability of C, given that G has occurred. So given that we're in the intersection of A and B, which is just 1 and 2, what's the probability that we get an outcome that satisfies C? 0. The only outcomes that satisfy C are 4, 5, and 6. And none of those numbers are in the intersection of A and B. So now, back down, the probability of C given G is 0. And 1/3 times 0 is 0. So again, we can see that before we even start. But if you start to go through the process just because maybe you don't see that, if you do it correctly, you should still get the right answer. I think that's important to know. The probability of the intersection of all 3 of these events is 0. And that also kind of shows you one way to approach a combination of more than 2 events. Combine them 2 at a time and then rename that event to kind of simplify things for yourself. Okay, but again, all of that work was kind of unnecessary. You should have noticed right from the beginning that it was 0. It's impossible for those 3 events to intersect. Try not to waste time. Remember, your AP exam is going to be timed. But you want to make sure you can notice those things. There we go. Next one, probability of event A intersect B. We just did that one. It was 1/3, right? All right, A intersect C. So again, we probability that A and C occur at the exact same time. How many outcomes are in both? None. 0. So I should get 0 again. And again, if I go through the process here, probability of event A times the probability of event C given A, that will be 1/2 the probability of event A times 0, because C can't happen if A has happened. So it again will be 0. Same thing for the next one. B given C is also 0. But also, if I go through the process, probability of event B, there's 2 outcomes that satisfy event B, so that's 1/3. But the probability of C happening, given that B has happened, is again 0, because in event B, there is nothing that satisfies event C. So it is still 0. So that's intersections, but what about unions? When we have the union of two mutually exclusive events, what would that look like? So that's the next two problems. Oops. So remember, union is an OR situation. So we have the probability that is in A or in C. So A is 1, 2, 3, and C is 4, 5, 6. So if my whole sample space is 1, 2, 3, 4, 5, 6, what's the probability that I roll a number that is either in A or in C? Well, that's everything that's in the sample space, 1, 2, 3, 4, 5, 6. That should be a 100% guaranteed thing to happen because we are combining two events that encompass the entire sample space. Let's go through the process anyways and see what happens. To calculate this, we would do the probability of event A plus the probability of event B minus their intersection if there is one. And we actually already did that before. Oops, that was supposed to be C, not a B. C. All right, so we already did that before. We saw here in part F, the probability of their intersection was 0. So we already know this is 0 here. We know A and C are mutually exclusive events. So we actually don't need to worry about their intersection at all. We know it's 0. We can leave that off. So the probability of event A, there's 3 outcomes out of 6, 1/2. And same thing for part C, 4, 5, and 6, that's 3 outcomes out of 6. So that's 1/2. And 1/2 plus 1/2 is 1. The probability of getting A or C is 1, meaning it's guaranteed to happen because if I combine those two events, I have every outcome possible. And last one, probability of B union C will again be the probability of B plus the probability of C minus their intersection. And we have again up here the probability of B intersect C we already found was 0. So that's just going to be subtracting 0. So it's not going to do anything because those two events are mutually exclusive. We can leave it off. Okay, the probability of B was not the same as the probability of A though. Going back up. Oh, I can't go back up. There it is. Nope, maybe. All right, B only had 2 outcomes out of 6. C had 3 outcomes out of 6. So 2 out of 6 is 1/3. 3 out of 6 is 1/2. And since I'm adding these, it might actually be better to leave them as a denominator of 6. 2 out of 6, 3 out of 6. Now they have the same denominator here, so I can go ahead and just add across the top and get 5 out of 6. The only outcome that would not satisfy this would be rolling the number 3. All right, part 7 here says we're referring to question 6 still. Are events A and B independent, mutually exclusive? Are events A and C independent, mutually exclusive? Well, let's see. A and B, let's start with A and B. Are they independent? So independent means the occurrence of one will not affect the occurrence of the other. And we're rolling a die here. So if I roll a die and it's in event A, a 1 or a 2 or a 3, does that affect the probability that we have rolled a 1 or a 2? Well, yeah, if I rolled a 1 or a 2 or a 3, the probability of rolled a 1 or a 2, the probability of B given A is equal to 2 out of 3. Whereas the probability of just rolling a 1 or a 2 in event B is 2 out of 6. If these two events were independent, then these two probabilities would be equal, and they're not. So they are not independent. Next question, are they mutually exclusive? No, they have overlap. 1 and 2 are in both events. So they are neither independent nor mutually exclusive. No and no. Next one, are events A and C independent, mutually exclusive? So looking at A and C. Let's see, are they independent? If I know that I've rolled something from A, does it affect whether or not I rolled something from B? So we look at the conditional probability and compare it to the regular probability. Does the probability of C given A Is it equal to the probability of just C? Well, let's see. If I look at A, if I know I've rolled something in A, what's the probability that it satisfies C? 0. Nothing in event A is an outcome that satisfies event C. That is 0. What is the probability of C then? The probability of C, there's 3 outcomes out of 6, so that's 1/2. Are they equal? No. So these are not independent events. Are they two mutually exclusive? Yes. All 3 outcomes in A are completely different than the 3 outcomes in C. So they're not independent, but they are mutually exclusive. So no and yes. And if you're wondering about that independent thing, how come rolling a die is not independent? It's because we're talking about a single roll of the die having commonalities between different events. If I was going to say that event A and event B were happening in 2 different rolls, then they would be independent, because the probability of rolling a die a certain way once does not affect the probability of rolling a die a second way, another way the second time. All right, but in this case, we're talking about rolling a die one time and seeing multiple things. Scrolling, there we go. Next thing, suppose probability of A is 0.4, the probability of B is 0.2. If events A and B are independent, what is the probability of A intersect B and the probability of A union B? So remember, for intersection, that's the probability of A and B. So we always say it's a probability of A times the probability of B given A. And if they're independent, the probability of B given A should be just equal to the probability of B. It would look like this. So all we do is multiply the probabilities together, 0.4 times 0.2, which is just 0.08. All right, next one. Their union should be equal to the sum of their probabilities minus their intersection. And we just found their intersection. It was 0.08. Okay, a lot of times in order to do the union problems, you have to do the intersection problem first. The only time you wouldn't need the probability of the intersection to find the probability of the union is if those 2 events were mutually exclusive, and they're not mutually exclusive. If they were mutually exclusive, then this number would be 0. So plug it in. Probability of A plus the probability of B minus the probability of their intersection is 0.4 plus 0.2 minus 0.08, which is 0.52. Next problem. A certain manufactured item is visually inspected by 2 different inspectors. When a defective item comes through the line, the probability that it gets by the first inspector is 0.1. Of those that get past the first inspector, the second inspector will miss 5 out of 10. What fraction of the defective gets by both inspectors? This sounds like something that has multiple things happening. And whenever I have multiple things happening and multiple probabilities kind of all over the place, I like to use a tree diagram to organize my thinking. I'm gonna kind of do that off the side here because there's not a lot of space right here. Let me get my page to move, maybe. There we go. All right, so we have this item. And let's see, it says a certain, when a defective item comes through line, the probability that it gets by the first inspector is 0.1. So it get by 0.1, which means the probability that that first inspector is going to notice it and throw it away probably, all right, just does not, is 0.9. Okay, then it says of those that get past the first inspector, the second inspector will miss 5 out of 10. So he's going to miss 5 out of 10, that's 0.5, which means he's not going to miss, he's going to throw away, get rid of, I'll just write does not again, the other 50%, 0.5. So what fraction of the defective gets by both inspectors? So what's the probability that it gets by the first inspector and it gets by the second inspector? Just multiply those two to get that combined probability. 0.1 times 0.5 is 0.05. 10. A smoke detector system uses two devices, A and B. If smoke is present, the probability that it will get detected by device A is 0.95, and by device B is 0.98, and by both devices is 0.94. So if smoke is present, find the probability that smoke will be detected by device A or device B or both devices. So it looks like we have all the probabilities that we need listed there. So I'm just going to go ahead and use my, my rule for the union of two events. The probability of A or B is what we're looking for is equal to the probability of A plus the probability of B minus their intersection. So we're not counting them twice. And they actually give us all of those probabilities here. So that's super. The probability of A detects it. Yeah, probability A detects it is 0.95. Probability of B is 0.98 minus the intersection, because that will definitely give me more than one. The intersection it says is 0.94. So grab my calculator, 0.95 plus 0.98 minus 0.94 is 0.99. 0.99. There's a 99% chance that at least one of the devices will detect the smoke. Part B, find the probability that the smoke will not be detected. Well, if there's a 99% chance that at least one of the devices will detect the smoke, then the probability that neither of them will detect the smoke should be just the complement of that. So we just take 1 minus the probability that at least one does detect it, and we get the probability that neither of them detects it.